Hello everyone, hope you are all doing fine. Welcome back to another lecture on electrostatics. In the previous lecture on electrostatics, we have learned about electric field. We have also discussed some of the examples on electric field. In this video, we are going to learn about motion of the charged particle in the uniform electric field. In the uniform electric field. So yes, my name is Vijay Krishna and you are watching up this channel. Let's get started. Okay, first let us understand what is uniform electric field. How do we represent this uniform electric field? Okay, so uniform electric field is the electric field whose magnitude is same everywhere in its space and the direction also pointed in the same direction. And the direction also pointed in the same direction. Okay, let me draw some of the uniform electric field diagrams. We represent uniform electric field with arrows in the same direction separated, that means parallel to each other, separated by equal distances. So this is the electric field. Direction is to the right and the spacing between the lines is all same. Okay, this is what we call it as uniform electric field. Okay, so you can represent this uniform electric field in this manner also. However, all the field lines should point in the same direction and spacing between two successive lines or consecutive lines should be same. So this is the representation of uniform electric field. Why do we represent the uniform electric field in this manner? Because to showcase the magnitude, length of arrow of all the arrows same, that represents the magnitude of electric field, and the direction of all the arrowheads are pointing in the same direction. This represents the direction of electric field is also same. So this is what we call it as uniform electric field. So we are going to use this uniform electric field and we place the charged particle in the uniform electric field and we study the motion of the charged particle when we place it in the uniform electric field. Okay, let's get right into the discussion. Okay, I'm going to take out this one. Okay, so let's take uniform electric. Actually, I want to mention one thing. The motion of a charged particle in uniform electric field has multiple cases. We can consider the case of case with gravity, without gravity. We can consider the case of electric field and the direction of motion of the charged particle in the direction of field or opposite to the direction of field. And we can also consider the direction of the motion of the charged particle perpendicular to the direction of field as well. So we can consider many number of cases according to the requirement. Okay, let's discuss some of the cases. Okay, so I'm going to consider uniform electric field here. I'm not going to take many lines which makes even a little complicated to make you understand. Okay, right. So I'm going to take uniform electric field. So these are the uniform electric field lines which are pointing in the same direction, separated by equal distances. I'm going to take few more lines. Okay, so this is the uniform electric field. As we have already learned, the electric field always flows from positive charge to negative charge. That means here we might have positive charge and here we might have negative charge. Field lines are flowing from positive to negative. Okay, I hope this field lines, uniform electric field, and how this uniform electric field have been obtained is clear to you, right? Okay, now let's move on to the actual discussion. Now I'm going to take a point charge, okay, of charge q and mass m. I've taken a particle of charge q and mass m. I'm taking the case where I have just placed this charged particle in the field. I haven't provided any initial velocity. Understand this one? This is its initial velocity is 0. It is initially at rest. This is the case that I am taking as of now. Okay, so this is the charged particle whose charge is q and mass is m, which is initially at rest. I've just placed in the field. Now what exactly field will do? This field, electric field, generates or gives certain amount of force to the charged particle. That force on the charged particle, F is equal to eq. F is equal to eq. F is equal to eq. What is this E? E is nothing but electric field. E is nothing but electric field. Okay, as I have taken the positive charge, the force will be in the same direction as that of the field. That means force on the charged particle is same as that of the electric field. Okay, direction of force and direction of field are both same. Okay, because of the force, this charged particle will accelerate. As there is force, there is acceleration. As there is acceleration, there will be force. So this force can also be expressed as ma according to Newton's second law. Now I can equate these two equations. Acceleration is a vector quantity. I'm going to consider the magnitudes only. So if I use the magnitudes, if I equate these two relations, EQ is equal to MA. EQ is equal to MA. From this relation, I'm getting the magnitude of acceleration as EQ upon M. So this is the expression for the acceleration of the charged particle when it is placed in the electric field of strength of electric field is E. Okay, of field strength E, where E is the electric field strength, Q is the charge of the charged particle, M is its mass. Now A is the acceleration of the charged particle. Its initial velocity is 0. As there is acceleration, the speed or the velocity keep on increases. So as the field is pointed in this direction, the force on the charged particle also must be in this direction. So the charged particle moves in this direction, right? Okay, so when you look at this equation, this electric field is not changing because it is uniform. Wherever you see the magnetic field, wherever you try to measure the magnitude of the electric field, it will give you the same value. Magnitude is same and the direction is also same. So E value is not changing throughout the space. Such a field that we have created, we called it as uniform electric field. And Q, charge of the particle, does not changes with the medium or even if it moves with the speed of light. Okay, mass M is the mass of the particle, which is also not changing as the particle is not moving with the speed of light. Okay, so as E, Q and M are constants, A can be considered as constant. A can be considered as constant, which can also be represented as uniform. That means this is the case of uniform acceleration. As you already know, whenever we come across a case of uniform acceleration, we can make use of kinematic equations. What are the kinematic equations? We have first equation, V is equal to U plus AT. S is equal to ut plus half at square, and v square minus u square is equal to 2as, where v is the final velocity, is the initial velocity, is the acceleration that we already know, t is its time, s is the displacement of the particle. As I have considered the case of u is equal to 0. Now in addition to considering this u is equal to 0, I am going to consider one more case also. That case is nothing but ignoring the gravity. In this case, I am going to ignore the gravity. I am going to discuss the taking the consideration of gravity case as well. Okay, right. So in this case, G is equal to also 0. We are ignoring the gravity. That means we are not going to consider the weight of the object or G value, acceleration along vertical direction. Okay, so we are going to consider only the acceleration that is caused by the electric field. Okay, so A is equal to EQ by M. Hope this is clear till now. The case that we have considered is also clear. I have just placed the charged particle in the field. I haven't provided any initial velocity, which is I have left the charged particle at rest in the uniform electric field. Okay, now the field itself exerted certain amount of force on the charged particle, due to which it has got accelerated, and thereby its velocity keep on increases. Okay, now u is equal to 0. I have considered the case of no gravity. No gravity. Okay, no gravity. So v is equal to u plus at. As I have taken initial velocity as 0, u is equal to 0, and this u2 can also be 0, and this u square also 0. Then what are the equations? V is equal to at, s is equal to half at square, and we have v square is equal to 2as. 2as. Okay, and we know the acceleration of the charged particle is eq by m. Eq by m. I'm going to write these equations here. V, velocity of the charged particle after some time t. After some time t, it is acceleration eq by m. A is replaced with eq by m. So eq by m into t. So this is the velocity acquired by the charged particle after time t. Now, if you want to find the displacement after time t, then s is equal to half, because u is 0, ut becomes 0, half a is nothing but eq over m into t square, into t square. I hope these two equations are clear. So this is again the equation for the electric field, velocity of the charged particle only. So you will get the same result as this one. Okay. So I have write velocity of the charged particle after some time t, and the displacement of the charged particle after some time t, when the particle is released from rest in the uniform electric field, and gravity is 0. Gravity is not considered. Gravity is not considered. This is one such case where we have got the equation for the velocity, for the displacement. I hope the steps that I followed, the explanation that I provided is clear to you, right? Okay, let's move on to the next case. Okay, this time I'm going to consider the gravity. I'm going to consider the gravity. In this case, u is again 0, but gravity is not equal to 0. That means there is acceleration due to gravity, which is acting in a downward direction, which is towards the center of the earth. Okay, so as you can see, the acceleration a is equal to eq by m. eq by m is to the right, I can consider this acceleration as x component, because it is pointed along the horizontal direction, along the x-axis. Now I have the gravity which is acting downward direction. This I can consider ay is equal to minus g. Ay is equal to minus g. You can even consider it as plus g if you consider the downward direction as positive. It depends on the sign convention that you consider. Okay, so ay is equal to minus g. I have considered upward as positive, downward as negative. As the g value is pointed in downward direction, I have considered the negative sign for the g value. Okay, so ay is equal to minus g. Hope this is clear. Right, now, so if ax is in this direction, ay is in this direction, I am going to write the kinematic equations for both x and y axis. So v is equal to u plus at. That means vx is equal to ux axt. Right? If you take the initial velocity 0, as the initial velocity is 0, its y and x components are 0, so ux is equal to 0 again. Ax is nothing but eq by m, so vx is equal to eq by m into t. eq by m into t. Now coming to y case, vy is equal to uy plus ay t. Here vy, uy, ay are not like v into y. It's v subscript y, u subscript y, a subscript y, which represents what y component of final velocity, y component of initial velocity, y component of acceleration. Time has no components. It is a scalar quantity, okay, which is always positive, which is always increasing. Okay, Vy, uy, ayt. Vy is how much? We don't know. We are going to find it out after some time t. Uy is again 0 because the particle is left at rest. Now ay is nothing but minus g t square, minus g t square. Okay, minus gt square. Okay, right, minus gt square. Now I have got vy and vx, vy and vy and vx. Sorry, I'm going to take these things out. Okay, vy and vx. Okay, now if I want to find the resultant velocity v after some time t, which is nothing but vx square plus vy square under root, vx square plus vy square under root, because these two are perpendicular components, so the resultant will be vx square plus vy square. We know vx, how much is it? Eq by m, that means e square q square by m square into t square. Okay, plus vy is nothing but gt square, which is nothing but g square t to the 4 under. So this is the expression for the velocity of the charged particle, which is initially left at rest in the uniform electric field, in the uniform electric field where gravity is considered. Gravity is considered. Hope the steps that I followed are clear to you, right? Right. Okay. Now let's move on to another case. Another case. Okay. So I've taken the same case with u is equal to 0, g is equal to 0, and u is equal to 0, g not equal to 0. I'm going to discuss another case by considering u not equal to 0, g 0, u not equal to 0, g not equal to 0. Let's discuss that one. I'm going to take this off. Okay. Keep the diagram as it is. I'm just going to change the equations. Right. Okay. So in the coming case, I'm going to consider u is not equal to 0, g is equal to 0. That means I have shot the charged particle with certain initial velocity. Okay, in the previous case, I have just left the charged particle at rest. The electric field itself, exerted certain amount of force due to which the charge is moving. But in this case, I have initially provided certain amount of velocity, and due to the force, its velocity again keep on increases. So u is not equal to 0, and I haven't considered any gravity here. That means gravity is absent, gravity is not considered. Okay, right. Now as I know, v is equal to u plus v is equal to u plus at. V is equal to u plus at. U is not equal to 0 in this case, so I'm not going to take this one as 0, as A is Eq by m, which we already know. Eq by m is in the same direction, so u plus Eq by m into t. Eq by m into t. So this is the velocity of the charged particle after some time t. After some time t. There is no much difference between the earlier equations and these equations. There is only one difference, that is this initial velocity is already there. Okay, initial velocity is already there. Now if you want to write the equation for the displacement in time t, s is equal to ut plus half at square, plus half at square. In this case also u is not 0, so ut I am keeping it as it is. Now half a is nothing but eq by m, and t is already there, t square. Okay, again the equations are again similar, but with this additional term. So these are the equation for the displacement as well as for the velocity. And we have one more equation, v square minus u square is equal to 2as. This is also similar. V square minus u square, keep it as it is. V square minus u square is equal to 2 into a is nothing but eq by m into displacement s. So this is another equation with initial velocity u. Initial velocity u. Gravity is not considered. Gravity is not considered. In the next case, we are going to consider the gravity as well. So in the next case, I'm going to take u is not equal to 0. That means particle is initially shot with certain initial velocity u, and g is also not equal to 0. That means the gravity here is working. It is not absent anymore. Okay. Now I'm going to take the same equations again. So this is ax, which is equal to eq by m, and this is ay, which is minus g, which is minus g. Okay, right? Now a net, that means kinematic equations. I'm going to write the equations directly. V is equal to, I'm going to write the equations along x and y directions separately. Rather, you can write the kinematic equations in vector form to avoid writing it for two times. But I want to explain it in a simple way. I'm going to divide the equations in two directions, x-axis and y-axis. I'm going to write the equations separately. Okay, so Vx is equal to ux plus ax t axt. Okay, now Vx is equal to, ux is how much? I have provided the initial velocity along the same direction, u. Okay, so u is in the x direction, plus ax is nothing but eq by m into t. So this is what Vx is. The Vx will not change, which will be as it is. Now coming to Vy, Vy is equal to uy plus ay t, plus ay t. As the particle is projected along the horizontal direction in the direction of field, its vertical component of velocity will be 0, right? Vertical component of initial velocity will be 0, as I haven't provided any velocity in vertical direction, y direction, up or down. Okay, so its y component of velocity will be 0, because the charged particle is projected along the x-axis, not along the y-axis, not along the y-axis. After some time, it may gain velocity in y-axis. That we are going to get the equation. Okay, so uy is equal to, even though the vertical component of initial velocity is 0, its final velocity will not be 0. Ay is how much? Minus g. Ay is minus g t. Ay is minus g. Hope this point is clear, right? Okay, right. Now Vy is equal to minus gt. Vy is equal to minus gt. Okay, so this is Vy, this is Vx. As you can see, even though the vertical component of initial velocity is 0, its final velocity is not 0, because there is acceleration due to gravity, which is pointing in the downward direction, which is giving additional amount of velocity in y direction. Okay, which is causing the increase in velocity in vertical direction, downward direction. So if I want to find the net velocity, v is equal to vx square plus vy square under root. Vy square under root. Now vy square under root. Okay, so if I know the vx value, which is u plus eq by mt whole square, plus I know the vy value minus gt, which is sorry, I know the Vy value minus Gt minus Gt whole square under root, minus Gt whole square under root. Hope this equation is clear to you, right? It is understandable, right? Okay. So u plus eq by m into t plus minus gt whole square. So this is the velocity of the charged particle after some time t, when the particle is shot with initial velocity u and gravity is not absent. Gravity is not absent, it is already there. Okay. So the question is, what would be the path of the charged particle? How does the charged particle move? Does it move along the straight line along the electric field direction, or does it move along the downward direction because of the gravity? No, it will not move in either of the direction. It is rather moving in a parabolic manner, something like this, because the motion of the charged particle is being influenced by both electric field and the gravitational field together. As an effect, as a result, the motion of the charged particle will be a parabola, as shown. Okay, motion of the charged particle will be a parabola. Hope these points are clear, right? right? Okay, let's move on to the next case. Okay, now in the earlier cases I have shot the charged particle in the direction of field, but in this case, in the coming case, I am going to provide the velocity. I'm going to short the charged particle perpendicular to the field. Perpendicular to the field. I'll draw the diagram so that you'll be able to understand it. Okay, right. Now, let's draw the diagram. So, uniform electric field. Uniform electric field. Okay. I may not be that accurate to draw the diagrams, but anyhow, all these arrows. Okay, sorry. Okay. Okay, so uniform electric field, all the arrows are pointing in the same direction and separated by equal distances. Let it be. So uh, okay, sorry, instead of drawing the lines in this direction, let's draw the diagrams, let's draw the lines in the vertical direction. Suppose like this, sorry, like this. Okay, so these are the field lines, electric field lines. The electric field strength is E. Electric field strength is E. Okay, which are pointing in the downward direction. That means here we have positive charge, here we have negative charge. Negative charge. Now what I'm going to do is I'm going to short the charged particle with certain initial velocity perpendicular to the field. Perpendicular to the field in the sense I have shot the charged particle of charge q and mass m, charge q and mass m with velocity u, with velocity u in the horizontal direction, which is perpendicular to the field. Field is in the downward direction, but perpendicular to the field I have provided the initial velocity. Okay, now there is velocity, initial velocity is not equal to 0 in our case, that I have already mentioned, but gravity is absent. I'm taking this case. Next time I am going to add the gravity as well. Okay, gravity is absent. Let us consider this case first. Let us learn this case and then we move on to gravity case. Okay, now what happens? Okay, now what happens? Okay, right. Now when you look at the diagram, the field is in downward direction. That means the acceleration of the charged particle along y-axis, e q by m, I have used the positive charge, so it always attracted by the negative charge. That means this negative charge is trying to attract the positive charge, attract the positive charge. As a result, the motion of the charged particle will be parabola, something like this. I hope I made the point clear here. This negative charge is always trying to pull the positive charge downward, because this electric field causing the force on the positive charge in the direction of the field. That means this field is pushing the charged particle, positive particle, in the downward direction, in the field direction, towards the negative charge. Hope my point is clear, right? Okay, now ay is equal to eq by m. As there is no gravity, just ignore it, I'm not going to consider it. Okay, so ay is equal to eq by m. Right, now velocity, if you consider the velocity equations, I'm going to write. So v is equal to u plus at. V is equal to u plus at. As the motion is confined to both x-axis and y-axis, I am going to write the equations separately. So v is equal to u plus at b is equal to u plus at again, but this is for x, x, x along x-axis, and this is for y, y, and y, 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 and y. Okay. Now, so Vx, Vx is equal to, I have already told you, I have projected the charged particle along the horizontal direction, along the horizontal direction. So this is x-axis, positive y, and this is negative y, right? So I have projected the charged particle along the x-axis. That means the initial velocity is pointed in the positive x direction, positive x direction. So Vx, Ux is nothing but u. I have already mentioned u is not equal to 0. That means there is initial velocity which is along the positive x direction. So Ux is equal to u plus Ax is how much? Ax is how much? Since the field is in y direction, there is no acceleration along the x-axis. There is no acceleration along the x-axis. Let me explain this point again to you. Field is in the downward direction. That means the force is in the downward direction. This force is accelerating the particle. That acceleration also should be in the direction of force. That is why the acceleration direction is along the y-axis, which is downward, negative y-axis. Okay. But as there is no force on the charged particle along the horizontal direction, along the horizontal in the sense x-axis direction, as there is no force along the x-axis, the x component of acceleration must be 0 times t. Okay, so this whole term would become 0. So Vx is again u. Vx is again u. Now coming to the y component, Vy is equal to uy. Uy, as I have projected the particle in the horizontal direction, its initial velocity component along y-axis is 0. Y-axis is 0. To make you understand it even better, I am going to write the vector representation of initial velocity. Initial velocity as a vector. As a vector. As it is projected with initial velocity u along x-axis, its y component is 0 j cap. 0 j cap. So ux is u, ux is u, uy, sorry. ux is ux is u, uy is 0. These are the two quantities that I've used in these equations. So ux is u, uy is 0, and ay is nothing but eq by m, which is to the downward direction. So minus eq by m into t. So Vy is equal to minus eq by m into t. Minus eq by m into t. Even though the cases are different, there may be multiple number of cases, different cases, but the strategy that we are using is simple. It is a two-step strategy. First thing is, we have to draw the diagram. We have to identify the accelerations, initial velocities. Okay, accelerations in the sense x component of acceleration, y component of acceleration. Initial velocities in the sense x component of initial velocity, y component of initial velocity. For the same object, there won't be two initial velocities, right? There won't be two different initial velocities. Rather, the velocity will have two different components, x component and y component, whereas the acceleration also will be of two components, x component and y component. We have to identify these components, and then it's a simple thing. Second step is using the kinematic equations. This is the logic behind working of all the examples, all the questions based on this concept. Okay, basic key point. It is a two-step concept, which is identifying the initial velocity vector or initial velocity x and y component, acceleration vector or acceleration x and y components, and then second step is using the kinematic equations. Okay, right. So Vy is equal to minus eq by m into t. Why did we put minus sign here? Because this y component of acceleration is pointing downward direction. As I have already mentioned, I always consider the upward direction as positive, downward direction as negative, rightward direction as positive, leftward direction as negative. I always use such sign conventions, these sign conventions. So I have put negative sign for y component. of acceleration. Okay, as the velocity component, when you identify the velocity of the charged particle here at this location, sorry, at this location, its velocity component will be this one, right? Its x component will be this one, y component will be this one. Vx is again u only. Vy is nothing but minus eq by m into t. Why minus sign is there? Because its component is pointing downward direction, negative y direction. That's the reason there is negative sign for the y component of velocity, right? Okay. Now, if I want to find the total velocity, I mean net velocity, magnitude of velocity. So, what is magnitude of velocity? V is equal to root over Vx square plus Vy square. Vx square plus Vy square. Okay, right. So, Vx square plus Vy square. Okay, right. Till now it is clear. If you substitute Vx here and Vy here, you will get the result u square plus e square q square by m square into t square root over. So this is the expression for the velocity of the charged particle after some time t in the given case. See, gravity is neglected here. We haven't considered the gravity. In the next case, we are going to consider the gravity as well. Okay, right. Hope this explanation is clear to you, right? So I'm going to make small changes to this explanation by for the next case, where in which I'm going to consider gravity as non-zero. That means gravity is not ignored, it is rather considered, it is rather significant. Okay, so gravity is non-zero, gravity is not equal to zero. Okay, so if you look at the diagram, okay, ay is eq by m, and in which direction ay, this is the electric field, this is the acceleration of the charged particle due to the electric field, due to the electric field, which is already we know, which is obviously pointing downward direction. Ay is in downward direction, which is due to electric field, which is due to electric field, right? Now there is another acceleration in this case, which is acceleration due to gravity, which is also pointing in which direction? Obviously in the downward direction. That means Ay due to gravity is also in the same direction. I'm taking the magnitudes only. I'm going to use the directions in the equations. Okay. So rather I'm going to use the negative sign here and here as well, because these two are pointing in the downward direction. These two are pointing in the downward direction. So if I have the gravity considered, then the equation would definitely change. Equations would definitely change. What is the net acceleration along y direction? Because both the accelerations are in the same direction, which is downward, That means minus g plus eq by m is the acceleration along y-axis. Acceleration along y-axis. Acceleration along y-axis. Hope this point is clear. Acceleration along y-axis. Okay, well and good. Okay, instead of writing eq by m in this case, I am going to write g plus eq by m. Is that okay? Right. So Vx is equal to ux axt. So what is x value? Ax is equal to what? 0, because there is no force along the x-axis. Both the forces are acting along the y-axis only. So x component of acceleration is 0. This will not change. The u will not change. It will remain as it is. It will remain as it is. Okay. Keep this. Sorry. Keep this as it is. Okay. X is equal to Vx. Is this clear? This will remain as it is. Now coming to this one, y component. Vy is equal to uy plus a by t. As I have projected the charged particle along the x-axis, its y component, initial velocity y component is again 0. This will remain as it is. So minus ay is how much? Minus of g plus eq by m. In the earlier case it was minus eq by m, but in this case minus g plus eq by m. So if I make use of that relation, so how do we do that? Sorry. Okay. Okay. So 0, right? Acceleration ay is nothing but minus g times, sorry, minus g times, I mean g plus eq by m, eq by m into t, ay into t. So vy is equal to minus g plus eq by m into t, into t. Now if you want to find the magnitude of velocity, you will have the basic equation here, which is v is equal to vx square plus vy square. V is equal to vx is again u square. Vy is g plus eq by m. So g plus eq by m into t whole square. Minus sign is already there, so whole square. Okay, so this is the net velocity, I mean the velocity of the charged particle after some time t, after some time t. Here vx will remain same, which is u, vx is equal to u, but vy has changed g times, I mean g plus. So I'm going to change this one. Okay, vy is equal to minus g plus eq by m, g plus eq by m. This is the y component of velocity of the charged particle for the given case. Do not forget the case. Initial velocity is not zero, which is pointed along the horizontal direction along the x-axis, whereas gravity is not ignored, it is rather considered, rather significant. So in such a case, ay is this one, and x component, y component, resultant velocity. Okay, hope the steps that I have followed are clear to you, right? Okay, the difference, I would like to give some more details about this concept. Listen, so g plus eq by m, right? As we have taken the charge as positive charge, these are the equations that works really well. What if I would have taken negative charge instead? Instead of taking the positive charge, I have taken negative charge. This time, let this charge be negative. Then what happens? In which direction it moves? It always moves in the direction opposite to the field, right? That means this negative charge will be attracted by positive charge. I'm going to draw the diagram here. See, let's say I have projected the charged particle in this direction. What kind of charged particle? Negative sign. Negative sign. So what happens? What happens? Here we have, sorry. Here we have positive charge. Here we have negative charge, right? Negative charge. Let's say I have projected a particle of charge minus q into the field perpendicular to the field. Then what happens? I projected the charged particle like this. Then what happens? In which direction? Does it move in this direction or in this direction? Which one is correct? Which one is correct? It will definitely move in this direction. This will be the correct. This won't be the correct one, because this negative charge will always be attracted by the positive charge. Negative charge will always be attracted by the positive, so the negative charge always moves towards positive charge, but not all at once. It slowly drifts towards positive charge. Okay, right? It will not move towards negative charge because of the repulsion. It moves towards positive charge because of the attraction. Then what happens? If this is the case, let's say negative sign that I've taken, in such a case, the motion of this, charged particle would be something like this. If it is minus q charge, same case applies, same equations. Only difference is sign changes. In the earlier case, I mean, another thing also changes. In this case, eq by m is positive. okay, and g is downwards. So the equations would be like, it will be like equations. I am giving you the entire details in the same diagram. Let's discuss it another. You know, let's take out this one. I hope the steps that I've followed are clear to you. I'm going to make use of the same diagram to showcase the direction of the negative charged particle motion, direction of motion of the negative charged particle in the uniform electric field that I've considered. Okay, right. So if I'm going to erase all these things. Okay, how does the equations change? Let's see. Let's see. Okay, so let us suppose I have projected the charged particle of negative charge minus q charge, minus q charge. If this is the minus q charge, then acceleration of y due to electric field is eq by m again, but upward, that means with positive sign, with a positive charge sign. Similarly, acceleration along y axis due to gravity, which is minus g only, which is always pointed in the downward direction. So the effective acceleration will be, acceleration a is equal to how much? eq by m, eq by m minus g, minus g. Okay, let's suppose I've taken the case where eq by m is greater than g. Acceleration of the charged particle due to electric field is more than, so quite quite possible this acceleration due to electric field is more than gravity. If g is greater than eq by m, if g is more than eq by m, then the charged particle motion will be in the same manner as that of the positive charge, same manner as that of the positive charge. Hope you have understood the steps. And the other point is, in the earlier case we have used the positive sign for the charge, for the charge, but in this case we are going to use the negative sign, we are going to use the negative sign. If you use both the sign conventions at a time, you'll get the wrong answer. Instead of using one sign conventions at a time, you'll get the correct answer. Let me explain how. I've taken this as a positive charge, positive sign, right? Instead, let us suppose let's say I've taken the negative sign as that of the earlier case. I've kept as it is, kept negative sign as it is. Now, as I've taken the negative sign, I can put negative sign to this charge, to this charge. This negative sign and negative sign, what happens? It will become positive. It will become positive. Hope my point is clear, right? So that's how you'll get positive sign, positive sign. And this acceleration due to gravity is always negative, which is pointed to the downward direction, right? Okay, so if you consider eq by m is positive minus g, a is equal to this one, a is equal to this one. If you substitute this acceleration, a y vertical direction, right? A y vertical direction, a y is g, ax is equal to again how much? 0. Ax is equal to 0 because there is no force along the horizontal direction. Ax is equal to 0. I'm writing the equations here. Ax is equal to 0, ay is equal to eq by m minus g, minus z, eq by m minus g. Okay, right? Okay, so can I write plus or minus g, plus or minus g, as when you look at this, um, what do we say? Okay, leave it as it is, eq by m minus g. Now if I substitute these relations into this equation, what am I getting? Bx would be same again, Vy would be eq by m minus g into t, eq by m minus g into t. If it is in downward direction, you can use positive sign here, no need to worry. You will get the sign from this expression, expression. Hope my point is clear. Okay, right. So next, next case, oblique projection. Oblique projection. Okay, in the next case, I'm considering oblique projection. Okay, I'm going to consider the field in the downward direction. Okay, in the downward direction, and the horizontal axis is this one. Vertical axis is, let's say, this one. Y axis, x axis, y axis and x axis. Okay, x and x axis. Right now I'm going to take one charged particle. Okay, I'm going to project this charged particle with an initial velocity u. With an initial velocity u. Okay, now charged particles charge is q, mass is m. Mass is m. Charged particles charge is q, mass is m. Okay, right. Mass is. Then what happens? As it moves in the field, as we know, here we have positive charges, here we have negative charges, right? As I have considered the positive charge, this positive charge is being attracted by negative charges, so due to which this charge will slowly moves towards down, moves towards down. Hope my point is clear to you, right? Okay. So it obviously follows the parabolic path. I have projected the charged particle with certain velocity at certain angle to the electric field. Certain angle to the electric field. This kind of projection is called oblique projection. Okay. So electric field is in the downward direction. Electric field is in the downward direction. Okay, electric field is in the downward direction, so the force on the charged particle also must be in the downward direction, because the charge that I've considered is positive charge. So acceleration of the charged particle along y-axis due to electric field is eq by m. Eq by m. Similarly, acceleration of the charged particle along y-axis due to gravity, oblique projection, gravity is there. Due to gravity, how much? G. These two electric field, the acceleration due to electric field is in the downward direction, and this acceleration due to gravity is also in the downward direction. So acceleration along y direction is eq by m plus g in the downward direction, minus in the downward direction, minus. Okay, in the downward direction. So you can consider the negative sign while using it in the formulas. Okay, now Ay is equal to this one. This is the effective acceleration. Now what about acceleration along x-axis? As I have already told you, as there is no force along the horizontal direction, the acceleration along x-axis is 0. Acceleration along x-axis, rather writing here, I'm going to write it here. Acceleration along x-axis is 0, right? Now let's make use of kinematic equations, or directly I'm going to write the equations as I have already derived the equations for the range, maximum height, time of flight, time of ascent, time of descent kind of formulas that I have already derived in kinematics, right? So if you can remember the formulas, it is great. If you are unable to remember the formulas, please go and check the details in the kinematics lessons. Okay, so you will be able to recollect it. Now, so as we already know, time of descent, time of flight. Time of flight is usually given by the formula 2u sine theta by g. 2u sine theta by g. Okay, so these are the formulas for the projection of the particle with an initial velocity u at an angle theta. At an angle theta, and the path followed by this one is parabola. Now maximum height is h, and time of flight is t, and maximum horizontal range is r. Is r. The general formulas for time of flight is t is equal to u sine theta by g, and maximum height h is equal to u square sine square theta by 2g, and range r is equal to u square sine 2 theta by g. These are the basic formulas. time of flight is the sum of time of ascent and time of descent. So you can even obtain the formula from obtain the formulas of time of ascent and time of descent from time of flight itself. So I'm writing the equation for the time of flight, which would help you to grab the to write the equation for time of descent and ascent. Both of them will be same. So time of flight. So instead of writing, as we have g only here, acceleration along y direction is g, which is to the downward direction. As we have only g, acceleration due to gravity, we have got these expressions, right? But in our case, it is different. In addition to the gravity, there is another acceleration which is also pointed in the same direction, that is acceleration due to the electric field. Due to the electric field, both of them are pointing in the same direction, that is agreed. Okay, but however, along with acceleration due to gravity, we also have acceleration due to electric field. So I'm going to use that expression. So instead of writing this equation as 2u sin theta by g, I'm going to write 2u sin theta by g effective, and h is equal to u square sin square theta by g effective, and u square sin 2 theta by g effective. This would help. Okay, so time of flight 2u sin theta 2u sin theta by g effective is how much? I mean g effective in the sense a net. A net is nothing but root over ax square plus ay square. Ax square plus ay square. As we already know, ax is equal to 0. This can be taken out. So a is equal to g effective is equal to ay square. Ay is nothing but eq by m plus g. As there is square, you can take out this negative sign. Eq by m plus g. Eq by m plus g. What if I would have taken negative sign, negative charge? In that case, minus eq by m minus eq by negative charge in the sense it will act in the upward direction, so this will be positive. Okay, this will be negative. In the earlier case, both of them are pointing in the downward direction. I have taken negative sign for both of them. Okay, but if the charge is negative, then the charged particle will move in upward direction, right? So a y due to electric field will be eq by m, which is positive, and g will be downwards, which is negative. This equation will change as minus eq by m minus g. So g effective is equal to eq by m plus g, as I have taken positive charge. Okay, so I can write eq by m plus g, and here also I can write u square sin square theta by 2 into eq by m plus g, and here also u square sin square theta by by g effective is eq by m plus g. Right? Hope I made the point clear here, right? Okay. So however, you will write the positive values for time of flight, maximum height, and range. So for negative sign, let's say I've taken the negative charged particle. In such case, what you will get is you will get g effective is equal to g minus eq by m. And you will get these equations like g minus eq by m, instead of writing the equation only for positive charge or negative charge. I'm going to write the equation for both together, something like this. These will be ultimate equations to find the range of the charged particle, maximum height of the charged particle, or time of flight of the charged particle. Okay, when the charged particle is projected at certain angle to the electric field or to the horizontal. Okay, now time of flight is equal to 2u sin theta by g effective. effective, G effective, which is 2u sine theta by G effective will be G plus or minus EQ by M, plus or minus EQ by M. And similarly maximum height, which is u square sine square theta by 2g, which is u square sine square theta by 2 into G effective. G effective is G plus or minus EQ by M. Okay, similarly for range is u square sine 2 theta by G, which is in G effective I'm writing. So u square sine 2 theta by G effective is G plus or minus EQ by M. So these are the ultimate equations for the electric field. Time of flight, maximum height, and the range when the particle is projected with certain angle to the electric field and with the horizontal as well. If the charged particle is positive, then you will use positive sign here. If the charged particle is negative, then you will use negative sign. So yes, that's it in this video. I hope the lecture that I have explained or the steps that I have followed are very clear to you. If you still find any difficulty in understanding, please comment below. If you really find the video is really helpful, please like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So yes, that's it in this video. Thanks for watching. See you in the next video.